All right, moving on. Our last lecture about sets, about set theory. And what I want to do is talk a little bit about infinite sets. So some things that we discussed earlier on in this set of lectures about set theory is we talked about the idea of equivalence, and we said sets A and B are equivalent, or another phrase that we used for that was one-to-one correspondence, right? So sets A and B are equivalent or in one-to-one correspondence if the number of if the cardinal number of A is equal to the cardinal number of B. In other words, if the number of elements in A is the same as the number of elements in B. The elements don't have to be the same, they just have to have the same, there just has to be the same number of elements in both sets, right? Okay. So that's A and B are equivalent. Another thing that we talked about is that a set is finite if its cardinal number is a whole number. It's infinite if it's not finite. Okay. So in this section, what we're going to do is talk about how to determine when infinite sets are equivalent. And so to begin with, we need to revisit this concept of the one-to-one correspondence, because if you have infinite sets, then you can't count up the number of elements in them, right? And even if you could, what would it mean to say that one set has an infinity number of elements and the other set has an infinity number of elements? What would it mean to say that those things that those numbers are equal to one another, right? So this is kind of a challenge. So we're going to revisit this concept of one-to-one correspondence, and here's how we're going to define it now. So we'll say two sets A and B are in one-to-one correspondence if we can pair the elements of the two sets so that every element of A is paired with exactly one element of B, and every element of B is paired with exactly one element of A. Okay, so if we can match them up one-to-one, then we'll say that they're in a one-to-one correspondence. And in the case that A and B are finite, this new definition agrees perfectly with this first bullet point, right? Since the only way that we would be able to match up the elements one by one is if the two sets had the same number of elements to begin with. And here's a picture. Here are some pictures to kind of further convince you of that. So let's say that we had one set A that's made up of the numbers 1, 2, and 3. And then let's say we have another set B that's made up of the numbers 1 and 2. Now, can we match those up one-to-one? Of course not, right? Can't match them up one-to-one. If we took 1 and matched it there, and then we took 2 and matched it there, well, that doesn't leave anywhere for 3 to go, right? You could say, well, why not just send 3 up here to 2 as well? And of course you could do that, but then that would not be one-to-one. Because this 2 over here is kind of linked up to 2 different numbers, right? So that's not a one-to-one map. That's not a one-to-one correspondence. Okay, let's say that A is the set 1, 2, and that B is the set 1, 2, 3. Okay, can we do a one-to-one correspondence this way? Well, no. We could send 1 to 1. We could send 2 to 2. We could send, but then 3 isn't getting matched up with anything, right? We're leaving 3 out of the picture. You could say, well, maybe we can send 1 to 3 or something like that. And, you could do that. But again, it would not be one-to-one. This is not a one-to-one correspondence because 1 here in A is being matched up to 2 different elements in B. So that's not a one-to-one correspondence. The only way you can get a one-to-one correspondence when you have 2 finite sets is if those sets have the same number of elements. Oh, and we can call them something else. Star, square, and circle. I mean, they can be anything. But now you can see easily that you can get a one-to-one correspondence, right? So yeah, in order to have a one-to-one correspondence, that means that we have to be able to match up the elements one by one. And if the sets are finite, the only way we're going to be able to do that is if the sets have the same number of elements. And so you may wonder, well, why are we talking about this new way to define it if it's just equivalent to our old way of defining it? Well, the reason is because it allows us to compare infinite sets. I'm missing a word here. So what's nice about this new definition is that it allows us to compare infinite sets. Infinite sets. Since we can't actually count up the elements of an infinite set, right? So in other words, in order to know if two sets are equivalent, in other words, the same size, or in other words, whether or not they have the same number of elements, or in other words, whether or not they have the same cardinal number or cardinality, right? In order to figure that out, to see if two sets are equivalent, we don't actually have to count up the number of elements in each set. All we have to do is be able to match up the elements of the set one to one. If we can match them up, then they must have the same cardinality. They must be the same size of set. Okay? And so this will allow us to compare sets that are infinite, because all we have to do is match up, if possible, match up the elements of each set, and then we can say that they're the same size, even if they're infinite in size. Okay? So with that in mind, let's remind us of a couple of our infinite sets that we went over. I can't remember if we went over this 2 or 3 lectures ago, maybe 4 lectures ago we went over these. I can't remember now, but let's remind ourselves of these things, right? So we've got the natural numbers. These are the counting numbers, 1, 2, 3, 4, 5, 6, 7, right? The positive whole numbers. We've got the whole numbers, which are the natural numbers, but with 0 thrown into the mix. And then we've got the integers, which are the positive whole numbers and the negative whole numbers, and of course 0 thrown into the mix. Okay. And then we have the kind of weird sets, right? The rational numbers, Q. This is the set of numbers that can be written as a ratio of 2 integers, right? So they're rational because you can write them as a ratio of 2 integers. In other words, it's the set of all numbers that can be written as fractions. Okay. And then you've got the real numbers, R, right? The real numbers are the set of numbers that can be written as decimals. Okay. So it should be pretty obvious that the set of natural numbers is an infinite set, right? This thing keeps going on and on and on forever. You can never find a biggest number, because let's say that you found a biggest number and you called it kazoo or something. I mean, I don't know. I'm just making stuff up. But let's say that you found the biggest number and it's kazoo. Well, you could always find the next number. You could say, well, kazoo plus 1 is bigger than kazoo, right? And it's also a whole number. So it must be. Anyway, the point is, you can never find the biggest natural number, right? This list goes on and on and on forever. And so the natural numbers make up an infinite set. Okay, so we're going to introduce a new symbol to describe the cardinal number or the cardinality of this set of natural numbers, right? So we use this symbol right here. This letter is the Hebrew letter Aleph. It's the first letter in the Hebrew alphabet, and it's pronounced Aleph. When we put a little 0 on there as a subscript, we oftentimes read the 0 as null, and so this would be called Aleph null. That's how we pronounce this symbol. So we use the symbol Aleph null to represent the cardinality of the natural numbers n. So in other words, the cardinality of the natural numbers, the cardinal number of the natural numbers is Aleph null. Okay. What's more is that any set that's either finite or has cardinality Aleph null is called a countable set. Okay. So it's a countable set as long as it's either finite or it has the same cardinality as the natural numbers, namely, right, Aleph null, this new thing that we're kind of defining. Okay. So what I'm going to do now that we have all of that background information, is I'm going to show you how we can show that 2 infinite sets have the same cardinality. And then I'm going to show you how we can show that you can have infinite sets that don't have the same cardinality, which is really kind of an interesting thing to try to wrap your brain around. But let's do this, right? So let's say that E is the set of even numbers. 2, 4, 6, 8, 10, 12, etc. Let's show that E can be put in a one-to-one correspondence with N. Okay, so that's actually not terribly difficult. All we have to do, I'm going to write out the elements of E, 2, 4, 6, 8, 10. And then I'm going to write, so this was E, okay? You can even make a little chart out of it. And then I'm going to write the elements of N down here. They're 1, 2, 3, 4, 5. And I can show, okay, so we can match these up like that. And in fact, let's say that this goes out to some number, we'll call it little n. We can come up with the rule for what this number has to be. Because notice, if I take this, if I compare these numbers, I have 1 and 2. I have 2 and 4. I have 3 and 6. I have 4 and 8. So it looks like the numbers on top are always 2 times the numbers on bottom, right? 1 times 2 is 2. 2 times 2 is 4. 3 times 2 is 6. 4 times 2 is 8. 5 times 2 is 10. N times 2 is 2n. Okay? And that's how we do it. So there is a one-to-one correspondence between these two sets, right? We can say, the one-to-one correspondence sends n to 2n, right? So that's it, right? So we can say n goes to 2n, right? That's the correspondence that does the trick. Okay, so that's easy enough. So we've shown that that this set, if you're paying attention, and I know that we've said the same things a whole bunch of different ways. So at this point, it's useful for us to kind of pause and think about what we just showed. What we showed is that this set, right, the set of even numbers, is the same size as this set, the set of natural numbers. And that's a little bit strange at first because it feels like, wait, the even numbers, that's only half of the natural numbers. So how could they possibly be the same size? Nevertheless, they are the same size because you can match up their elements one-to-one. You can put them into a one-to-one correspondence. And as we saw on the previous page, right, the only way you'd be able to do that is if the sets were the same size, right? So anyway, the set of even numbers, there are just as many even numbers as there are numbers, which is kind of weird, right? And this is kind of the crazy thing about infinite sets. But yeah, there are just as many even numbers as there are numbers, okay? If you tell me, yeah, okay, so that's that, right? Another thing that I'll point out, and this has to do with your homework, right? In this example, I phrased the problem by saying show that this set can be put into a one-to-one correspondence with this set. But there are a lot of ways that I could have said the same thing. I could have said show that E is countable, right? Because what does it mean to be countable? To be countable means that you have that either the set is finite or its cardinality is aleph null. Well, what other set has cardinality aleph null? The natural numbers, right? So to show that E is countable is to show that E has the same cardinality as the natural numbers. Well, how do we show that E has the same cardinality as the natural numbers? We show that there's a one-to-one correspondence between E and the natural numbers. So this is asking you to do exactly the same thing. If I say show that E is countable, I'm saying show that E can be put into one-to-one correspondence with the natural numbers. Okay? Or I could have said show that the cardinal number of E is equal to the cardinal number of N, and I'm missing a little parenthesis there, right? But I could have said show that the cardinal number of E is the same as the cardinal number of N. Same thing, right? So how do you show that? You show that you can put them into a one-to-one correspondence. Or I could have said show that E has cardinal number aleph null. How do you do that? Well, you put E into a one-to-one correspondence with another set that has cardinality aleph null. And N is such a set, right? So again, you show that you can put the sets into a one-to-one correspondence. So all of these things mean the same thing, and I'm just giving you a heads up because, when you encounter these kinds of instructions in the homework, they're all asking you to do the same thing, Okay. So for example, in number 2 it says, show that z is countable. What is z? Z is the integers, right? That's the positive and negative whole numbers plus with 0 thrown into the mix. And our task here in example 2 is to show that the integers, show that z is countable. Well, what does that mean? What does it mean? It means that we can put z into a one-to-one correspondence with n. Okay? So let's see if we can come up with a one-to-one correspondence. I'm going to switch the order. In this one, I put e on top and n on bottom. I'm going to switch that up, and I'm going to put n on top, and then I'm going to put z on bottom. Okay. So n I know is going to be 1, 2, 3, 4, 5, and so forth. Now z is a little bit trickier. So I'm going to do a little scratch work, right? So z is -3, -2, -1, 0, 1, 2, 3, and so forth. Okay? If I start to list here, 1, 2, 3, 4, 5, because those numbers are all integers, right? So if I start to list 1, 2, 3, 4, 5, well, I'm never going to get to the end of that list, right? And that's a problem because I also have to somehow sneak 0 and -1 and -2 into the list as well. So that's probably not a great plan. I think a better thing to do, what I need to do is I need to be able to list all of the numbers without using these dots in front. Well, I can kind of have dots on one side, but not on the other side. But here's the trick. They don't have to be listed in order. I don't have to list them in order. So what I think would be best is if I started at 0, and then I listed 1, and then I listed -1, and then 2, and then -2, and then 3, and then -3, like that. Right? If I listed them like that, then I would get all of the numbers on the list, right? So that's how I'm going to list z. 0, 1, -1, 2, -2, and let me do a couple more just to make it perfectly clear. 3, -3. Okay, this is how I'm going to make my one-to-one correspondence. Okay, now this is going to continue on and on and on. When I get to, let's say I get to n here, and let's say that n is an even number. If n is even, what is it getting mapped to? Notice that all the even numbers get mapped to, positive numbers. 2 gets mapped to 1, 4 gets mapped to 2, 6 gets mapped to 3. So it looks like they're all getting mapped to like their number divided by 2, right? 2 divided by 2 is 1, 4 divided by 2 is 2, 6 divided by 2 is 3. So it looks like this is just getting sent to the number divided by 2. But now if n is even, then n plus 1 is odd. And what's n plus 1 going to get sent to? So what are all the odd numbers getting sent to? Well, 3 gets sent to -1. 5 gets sent to -2. 7 gets sent. So they're all getting sent to negative numbers. And kind of using the previous work as a clue, if I divide them by 2, well, if I divide 3 by 2, I get 1.5, right? Not 1. If I divide 5 by 2, I get 2.5, not 2. So it seems like, but if I subtract 1, if I do 3 minus 2 and then I get 2, and then I divide that by 2, I get 1. If I do 5 minus 1, I get 4, and 4 divided by 2 is 3. If I do 7 minus 1, I get 6, and 6 divided by 2 is 3. So I think I'm doing the number. I'm doing the number, which is n plus. So let me do some scratch work. So I do the number, which is n plus 1. Then I'm subtracting 1 and dividing by 2. But n plus 1 minus 1 is just n, right? So this is still just n over 2, right? So I get this pair, right? I get this pair of the same number. One of them's positive, the other one's negative, right? Same number, but one's positive, one's negative. Same number, one's positive, one's negative. Okay. But anyway, that's how we map it. So if n is even, you send it to n over 2. If n is odd, you send it to negative n minus 1 over 2, right? Something like that. But there's our one-to-one correspondence. Okay, so z is also countable. That's interesting. Give me a second. Okay, I wanted to mention something else about that last example. So instead of taking n all the way out to n, what if we were interested in, like, how do we go the other way around, right? Like if I'm trying to map 0 somewhere or 1 somewhere, how would I do that? So let's say that I get up to n here. Where is n going to get sent to? Well, again, if n is even, n is going to get sent to 2n. Or maybe I'll use a different letter so it's less confusing. Where does k get sent to? K gets sent to 2k. And then where does so if this is k, then this one would be negative k, right? Negative k. Where does negative k get sent to? Negative k gets sent to, it gets sent to 2k plus 1. I'm giving you this alternative way to think about it, just because in the homework you might have some homework problems that say, you know, use what we did in example 2 to do blah blah blah, and so I just wanted to make sure that you had this kind of alternate way to think about it. But this still works, right? It's like, so if k is, and actually k doesn't even need to be an even number. It could be any number. So let's say k is 13, right? Where is 13 going to get sent? 13 is going to get sent to 2 times 13, which is 26, right? And then the next number on the list would be negative 13. Where is negative 13 going to get sent? Negative 13 is going to be sent to 2 times positive 13 plus 1, so that's 26 plus 1 is 27. And you can verify that it works down here too, right? Like when k is 2, it gets sent to 2 times 2, which is 4. When k is negative 2, it gets sent to 2 times positive 2 plus 1. That's 2 times 2 is 4 plus 1 is 5. Okay? So the stuff that I put in red is an alternative way to think about the same thing, and it's that might come in handy. Okay, so we've shown that there are just as many integers, or sorry, there are just as many natural numbers as there are integers, which is kind of crazy, right? Because it seems like, again, there should be twice as many integers as natural numbers, right? Since it includes all of the natural numbers plus all of the negative natural numbers. So that's kind of crazy that we were able to show that there's a one-to-one correspondence. But there is a one-to-one correspondence, right? You can always match up those elements one by one. Well, okay. So now here's the thing that's really crazy to me. Q is also countable. What is Q? Q is the set of rational numbers, right? It's the set of numbers that can be written as a ratio of 2 integers. So it's the set of all fractions. So the fractions are countable. They make up a countable set. How is that possible, right? Because if you think about it, between any 2 fractions, you can always find another fraction, right? Like between 1/2 and 1/2 and 2/2. Right? You can always find a fraction. 3/4 is right in between them. And between 1/2 and 3/4 you can find a fraction, right? You can find, so what's between 1/2 and 3/4? Well, if I take it down to like eighths, 1/2 is 4/8 and 3/4 is 6/8. So something right between them would be 5/8, right? And you can always do that. You can always find a fraction so given any two fractions, you can always find a fraction in between them. So it seems like they're very, very dense, right? Like there's so many fractions. How in the world are we going to make a one-to-one correspondence between the fractions and the whole numbers, the natural numbers? And one thing that you may have realized by now, if you haven't realized it yet, then let me say it explicitly. That is that if you can make a one-to-one if you can make a list of all the numbers, if you can write down all of the elements of a set, right? If you can make a list of all of the elements of a set, then that is equivalent to being able to put them into one-to-one correspondence with the natural numbers. Why? Well, because if you can make a list of them, then you just match the first thing on the list to 1, and you match the second thing on the list to 2, and you match the third thing on the list to 3, right? So to show that Q is countable, all we have to do is be able to write down all of the fractions, right? But how to do that? How do you do that, right? So like one thing that you might think of to try to write down all the fractions, you could say, well, I could start with like 1 over 1, and then go to 1 over 2, and then go to 1 over 3, and 1 over 4. And look, the problem with that is that this is never going to stop, right? Because you can keep letting that denominator get bigger and bigger and bigger. And the problem is that list is not going to contain all of your fractions, because it's not going to contain things like 5/8, right? It's not going to contain any fractions where your numerator is a number different from 1. So this won't work. So how in the world do we do this? How do we make a list of all of the fractions? Well, here's how it works, okay? So I'm going to give you the answer, and it's a crazy thing, but here's what we can do. First, we're going to start by making a chart, and then we'll turn the chart into a list. And here's how we make the chart, okay? So I'm going to change the numerator across the top row and keep the denominator the same. So 1 over 1, 2 over 1, 3 over 1, 4 over 1, 5 over 1, and so forth. And then down the column, I'm going to change the denominator but keep the numerator the same. 1 over 2, 1 over 3, 1 over 4, 1 over 5, and so forth. And then I'm going to fill in the rest of the chart, right? So here I should have 2 over 2, and then 3 over 2, 4 over 2, 5 over 2. Here I would have 2 over 3, 3 over 3, 4 over 3, 5 over 3. Okay, hopefully you see how this is working. So 2 over 4, 3 over 4, 4 over 4, 5 over 4, and then 2 over 5, 3 over 5, 4 over 5, 5 over 5. Okay, and this thing is going to continue on and on and on, right, forever, in every direction, right? It's going to continue going on and on and on. This chart contains all of the fractions on it, right? For example, the number 174 over 243 would be in the 174th column and the 273rd row, right? Or other way around, I'm sorry. So let me write it down. So let's say that you wanted the number 54 over 75, right? Is that number on the list? Yes, it's in the 54th row, and the 75th column, right, is in, so maybe I'll say this. So maybe I'll say, so note, all fractions are in the chart, right? For example, 54 over 75 is in the 54th row and 75th column. right? It's in the intersection of the 54th row and the 75th column, right? So and you can do that with any fraction you like, right? They're all in the chart. Now the question is, how do we make a list out of that? Because this isn't a list, this is a chart. This is like a two-dimensional list. How do we make a one-dimensional list out of it? Well, here's how. Your first inclination might be, well, I'll just start in the top row and I'll go all the way to the end of the row. But the problem with that is that you're never going to get to the end of the row, right? It keeps going on and on and on forever. Or you might think the same thing about going down the first column, but you're never going to get to the end of the first column. That's actually what we started writing up here. Okay, you're never going to get to the end of that first column, so you're never going to make it to the second column. So the trick is, and this is so genius, I'm not the one who came up with this. The person who came up with this was a guy named Georg Cantor, and he was a great genius, okay? But here's the simple genius of this, is that you go through diagonally. So you start in the top corner, and then you kind of snake your way through like this. Okay? Because notice that by doing it this way, you always reach the end of a diagonal. And so you're able to swoop around and get all of the numbers. And so if you swoop through this way, then you're going to end up capturing all of the numbers in the chart. And therefore, you will have gotten all of the numbers on the list, right? And so this keeps going, right? But that's how you do it. You swoop through like a diagonally, like a snake. Okay? Now, the thing is, though, that in order to put this into a one-to-one correspondence with the natural numbers, we can't have any repeats in our sets, right? And here we have a bunch of repeats, like 2 over 2 is 1. That's the same thing as 1 over 1, right? So when we make our list, we'll start to, so here I'm going to put n, and then I'm going to put q, all right? So n, 1, 2, 3, 4, 5, whatever. When I make the list of rational numbers, I'm going to skip over any repeats. So I'm going to reduce all of the fractions, and then I'm going to skip over any repeats. So like 1 over 1 is the same as 1. 2 over 1 is the same thing as 2. 1 over 2 can't be reduced. It's 1/2. 1 over 3 can't be reduced. It's 1/3. 2 over 2, though, that's the same thing as 1, and it's already on the list. So I'm going to skip that 1. So I'm going to skip this one, right? And then move on to 3 over 1, which is 3. Then I'm going to go to 4 over 1, which is 4. Then I'm going to go to 3 over 2, which can't be reduced. You could call it 1/2 if you like, but you can't really reduce it. 8 would go to 2/3. 9 would go to 1/4, and it's not on the list yet. I'm going to continue this chart. I'm just going to make a second row. So 9, 10, 11, 12, 13, 14, whatever. Okay, so where did we leave off? 1/4, and then we'd go to 1/5. And then we go to 2/4, but 2/4 can be reduced. 2/4 reduces to 1/2, and 1/2 is already on my list, so I'm going to skip that one. 3 over 3 reduces to 1, and that's already on the list, so I'm going to skip over that one. 4 over 2 reduces to 2, and 2 is already on my list, so I'm going to skip over that one. 5 over 1 can't be reduced, and so it goes to 5, right? And then next, I guess, would come 6 over 1, so it would be 6. And then you'd go down to 5 over 2, which is not on the list yet. And then you'd go down to 4/3, which is not on the list yet, right? And then you'd go on and on and on forever. Okay, but this is how you get a one-to-one correspondence. Notice that the fractions are not in order. They're nowhere close to being in order from smallest to largest. But nevertheless, you're going to end up with all of the fractions on your list, and you're going to end up with a one-to-one correspondence between those fractions and the whole numbers, right? So you've got this one-to-one correspondence going on. I'm not going to draw in all the arrows. But there you go, right? So there are as many natural numbers as there are fractions, which is crazy. So now at this point you might be thinking like, so maybe this is just true for any infinite set. Maybe all infinite sets are the same size, right? They're all just infinite in size. Maybe they all have cardinal number aleph null, right? Right? Because that's what we've shown. We've shown that n of n, right, is equal to n of z, which is equal to n of q, which is equal to aleph null. I'm not very good at writing aleph, but there you go, right? That's what we've shown so far. So you might be thinking, well, maybe any infinite set is going to have cardinality aleph null. And then here's where we get this crazy thing. The real numbers are not countable. The real numbers cannot be put into one-to-one correspondence with the natural numbers. The real numbers do not have cardinality aleph null. The real numbers have a bigger, the cardinality of the real numbers represents a bigger infinity than the infinity of the natural numbers, which is weird, right? It's like you're used to thinking of infinity as just like, oh, it just means it goes on and on and on, right? But there are infinities of different sizes, which is kind of crazy, right? But let's prove it. Let's prove it. So we'll show that the real numbers are not countable. So we'll show that the real numbers are not countable. Here's how we do it, okay? So first, we assume that they are countable. So suppose that R is countable. All right, so suppose that R is countable. What that means is that you'd be able to list all of the decimal numbers, right? Then you'd be able to list all decimal numbers. Okay, now here's what we're going to do. We're going to show you that no matter what list of decimal numbers you give me, it's always incomplete, right? We're always going to be able to find a decimal number that's not on the list, right? And then that's going to show a contradiction, right? So if we assume that R is countable, then we should be able to come up with a list of all the decimal numbers. But then we're going to show that no matter what list of decimal numbers you give me, the list is incomplete. And therefore, this assumption must be wrong, right? It must not be the case that R is countable, and therefore R is not countable. So suppose that R is countable, then you'd be able to list all decimal numbers. But we can always find a decimal number or find a number not on the list as follows. Okay, so let's say that you've got this list of decimal numbers, okay, and we'll go digit by digit, right? So if the first decimal place of your first number is a 1, then we'll make our decimal number that's not on the list, we'll make it a 2. If the first decimal of your decimal number is something different from 1, then we'll make ours a 1. Then we'll make our first decimal place a 1. And then we'll go through the list. So the second decimal place we'll do the same way. The third decimal place we'll do the same way. And what we'll end up with is a decimal number that's not on the list. So let's say that this is your list, right? Let's say that you've got, so let's say that this is your list of numbers. So you have 0.13259, whatever, and it keeps going. And then you've got 0.2 0.04040, and then you've got 0.512 53, and then you've got 0.12515, okay, and so forth, right? So you've got all these numbers on this list. So looking at the first number on the list and looking at the first decimal place, it's a 1. So we're going to make ours a 2. So our number is going to be 0.2, since that was a 1. Looking at the second number on the list, it's a 4. So we're going to make our second decimal place a 1. Looking at the third number, the third decimal place of the third number is a 2. So we're going to make ours a 1. Looking at the fourth decimal place of the fourth number, it's a 1. So we're going to make ours a 2. Okay, and we're gonna continue on with this process forever and ever and ever with every number on the list. So the next number on the list might be 0.11111. So we look at the fifth decimal place of the fifth number, it's a 1, and so we make our decimal place a 2. Okay, and this is going to continue forever and ever and ever. So is this number on the list? Is our number on the list? And the answer is no. Why not? Could it be, for example, the 99th number on the list? No, right? So could it be, for example, the 99th number? Right? And the answer is no, because if the 99th decimal place of the 99th number on the list is a 1, then the 99th decimal place of our number is going to be a 2. If the 99th decimal place of the 99th number on the list is something different from 1, then the 99th decimal place of our number is going to be 1. And so the 99th decimal place of our number is going to be different from the 99th decimal place of the 99th number. That's how we're constructing our number, right? We're constructing it specifically so that it can't be on the list, right? So could it be the 99th number? No, because the 99th decimal place of our number is different from the 99th decimal place of the 99th number on the list. Okay? All right, so since this list is incomplete, that tells us that our assumption must have been wrong, and so R is not countable. And in fact, even if you put this new number that we make, even if you put that onto the list, we can still do this process again and find a new number that's not on the original list, right? So, so the list is incomplete. And that contradicts the assumption that R is countable. Okay, that's a tricky argument for sure. It's a tricky argument. So if your head is spinning a little bit, don't feel too bad. Don't feel too bad about that. I have this video that does a really good job of illustrating all of the proofs that we've gone over in this lecture. And so I would highly recommend that you watch that video. And it also talks about something called the continuum hypothesis, which is a really interesting idea to consider. And basically what it has to do with is, okay, example 4 showed us, this last example showed us that the cardinality of the real numbers is greater than Aleph null. It's greater than the cardinality of the other infinite sets that we know about. And so a good question would be, are there any sizes of infinity between Aleph null and this new cardinality? And that's basically what the continuum hypothesis has to do with. But again, watch this video. I'm going to include it in today's module, or in the module with this lecture, because you should absolutely watch it. I think it'll help you to understand this argument a little bit better, and it's just a really cool video. So definitely watch it. And that's all I have to say about infinite sets. They're really interesting.